So in this lesson, what we're going to look at is what we talked about last time in class regarding the rate constant or the rate equation, the rate law. All of those things are built into this right here. The rate equation, the rate law. What we're going to talk about is for this chemical reaction right here, when N2O5 decomposes into NO2 and O2. The problem is right now, this is not a balanced equation. In order to balance it, we're going to need to put a 2 in front of this, a 4 in front of this. And now we have a balanced equation. We have 4 nitrogens, 10 oxygens, and 10 oxygens. This is important, but not so much for the rate equation, but more so for understanding what's going to take place. We also know that the rate law for this reaction has to have been developed experimentally. So somewhere along the lines, people have decided that this is the rate law. Rate equals K times the concentration of the N2O5. The exponents on this thing, as we look at it right now, there is nothing written. So this is going to be implied to be a 1. If that is a 1, then we know that no matter what happens throughout this entire reaction, the concentration of this stuff right here, this concentration of N2O5 is going to be the determining factor of this rate. K is a constant for a given temperature, and so we're going to look at that and see what takes place. A couple other reminders that as we look at this, we now know that the order of this reaction is going to be based upon the total sum of all of these exponents. Since there's only one exponent in this rate equation, then the order of this is going to be a first order reaction. This first order reaction tells us a lot of other information that we'll get to here in just a few minutes. So a couple things regarding K. K is the proportionality constant. If it's a first order reaction, the units of K are always going to be 1 over the time. That can be 1 over seconds, it can be 1 over minutes, it can be 1 over hours. Whatever the case may be, those will be the units on K for a first order reaction. For a second order reaction, the units of K are always liters over moles times time. So that would be like an inverse of molarity, liters per mole per second, or liters per mole per hour. So it's liters over moles and time on the bottom. Hopefully you'll start to understand why, if we're talking about the rate, that is, it has to have some unit of time that we're going to be measuring. So in this case, if it's seconds, if it's hours, if it's minutes, for a second order reaction, it's going to be liters over moles and some unit of time underneath. For a zero order, the units will always be just molarity over time, or molarity with 1 over time. So it's moles per liter second, or moles per liter hour. So these went to this, these go to this. All right. Again, once I have data that was able to be used to determine whether it's zero, first, or second order, I can then solve for the value of K. All we have to do is plug in everything we know. We'll know the rate, we'll know the concentrations, we'll know the exponents, and so we can just plug everything in and do math to solve for the value of K. As we continue on, we're just going to do a couple sample problems together. We're going to determine the rate equation for this balanced equation. What we have done is we have taken data where they show us 5 different experiments have been done. Experiments 1 through experiment 5. Each of these experiments had an initial rate, this initial rate that's right here, for 5 different reactions. This is the rate of reaction immediately when the reaction starts. We also have the initial concentrations of each of our reactants. So this is the concentration. It has nothing to do with these coefficients right now. A lot of people think that in kinetics, when they start to look at this, we're going to look and say, oh, the rate law for this, these are our 2 reactants, so the rate should be, this is what they assume, this is not correct. They say the rate is going to be NO squared and O2, because that's the coefficients in front of it. That is not necessarily the case. What we're going to need to do is look at our experimental data and figure out what actually happens. So remember, if it's first order, changing the concentration will change the rate. If it's first order, changing the concentration by doubling it should double our rate. Now, there's a mathematical way to look at these. I think you should be able to do these mental math. So the first thing I'm going to do is I'm going to compare this 0.20 and this 0.20. So we see that the concentrations of NO are going to stay the same. These stay the same. But what happens to the concentrations of O2? They are doubled. If those are doubled, what happens to our rate out here? Now, mathematically, most of you should be able to realize that this is really, really close to doubling. So we're going to check one more time. If I compare 1 with 3, I have kept the concentration of the NO constant, but my O quadruples. And what happens here? Again, when I quadruple these, 0.28 times 4 is about 0.114. It's not exact, but it's really, really close mathematically. If you do that on your calculator, if you divide 0.114 divided by 0.114 divided by 0.028, you get 4.07. So these two values are close enough to times 4. This was quadrupled, this quadruples. So with respect to the oxygen, we know that that's going to be first order. Because when I double the concentration of O2, when I double this concentration here, I double my rate. When I quadruple the concentration, I quadruple my rate. All right? So now let's look at it with the other things. So let's erase these, and we're going to compare different substances. So now when I look at what happens when I keep the concentration of oxygen the same, so I'm going to look at 2 and 4. The oxygen stays the same, but the NO is doubled. NO is doubled, oxygen is the same, and what happens to our rate? It goes from 0.057 to 0.227. Again, if you divide those two values, this is about times 4. I have doubled my rate, doubled my concentrations of NO, and I quadruple my rate. If I look at it in another place, just to make sure, I want to look at one other one where these two stay the same. And what happens here? It's quadrupled, going from 5 to 4. From 0.01 to 0.04. Again, that's quadrupled. So what in the world happened here? When you divide those two values, when I take 0.227 divided by 0.014, this is 16 times greater. All right? So when I quadruple this, 4 leads to a times 16. Hopefully you'll recognize that this is indeed going to be second order in respect to the nitrogen oxide, NO. So even though we assumed this and we thought, hey, that's what it's going to be, that's going to be our answer, the actual fact is it's only because of the data that shows up. So our data has to be what determines these exponents. So my final answer is indeed this that we predicted from the balanced equation, but you can't always make that assumption. That is not a valid assumption to make right away. So what we'll do next is one more sample problem with these where we'll look at the initial concentrations, see what happens to the rates as we do different things to these reactions. My apologies for my writing instead of it being typed out. I think you'll be able to read these okay. So the initial concentrations of carbon monoxide and and nitrogen dioxide are given along with an initial rate. In experiment 1, we took these concentrations that are here given, and we see a rate of 3.4 times 10 to the negative 8th. For the first comparison, if I look comparing reactions 1 to reaction 2, carbon monoxide stays the same, but nitrogen dioxide, that rate is doubled. Sorry about the inappropriate scientific notation, but it just makes it easier to see these numbers this time. So for this is being doubled from 0.350 to, so here, look at it this way, from 0.350 to 0.7, that's doubled. And as I look at that being doubled, what happens to my rate? It's also being doubled. So in respect to the NO2, I think it's going to be first order, because when I double the rate, I double the initial concentration, I've doubled my rate. Just to make sure, let's look at another one where I go from here at 0.350 to here at 0.175. Hopefully you recognize that this is being cut in half. I kept these constant, and this is being cut in half. what happens to my rate when I cut the concentration in half? It is also cut in half. So yes, definitely this is going to be first order in respect to the NO2. So now I need to compare and keep other things constant. So this time I'm going to compare 1 with, that was supposed to have changed colors, 1 with 4. Notice that my concentration of the NO2 this time is staying constant. With that being constant, I'm not changing its concentration. But what happened to my concentration here? Hopefully you have some understanding of scientific notation, and you'll see that 5.1 times 10 to the negative fourth doubled is 1.02 times 10 to the negative third. This would be the same as 10 times 10 to the negative fourth. So it's being doubled. And what happens to my rate? When I compare 1 with 4, my rate is again doubled. So again, it looks to me like with respect to the carbon monoxide, it's going to have been first order. But just to make sure, we can do another one. We can compare 1 with 5. In this case, this is being tripled, and this is staying the same. And my rate from 3.4 to 10.2 is indeed being tripled. So these are the two orders of the reaction. So my rate law would look like this. It would be the rate is equal to K times the concentration of the carbon monoxide times the concentration of the nitrogen dioxide. And this is overall second order. The last thing that I'm going to mention, I'm not going to go into a whole lot of depth here. I'm going to try to keep this message under 15 minutes. But is what's called integrated. Mr. Martin can't type, so we're going to try to fix that real fast. It is not integrated, it is integrated. There's not supposed to be an R there. The integrated rate law is calculus based. It is an integral. So again, you don't need to know all the information. That's why I wrote blah, blah, blah. What do we need to know? So there's a couple mathematical things that you need to keep in mind. First is this thing called ln, which is the natural log. It's in the base system of E, it's base E. And if you see R inside of square brackets, this R in square brackets is going to mean that it's the concentration of reactants. It will put either a subscript T or a subscript 0 for what time that is looking at. Like when are we talking about that concentration? So what ends up happening with these is we're going to end up looking at this mathematical equation that has to do with the natural log of a ratio of the concentrations. So you guys know what ratios are. Ratios are comparing time A to time B. So the mathematical expression for this, to get all the way down to it, is that for a first order reaction, the first order reaction is going to look like this. It is the natural log of the concentration of the reactants at time t divided by the concentration of the reactants at time 0 equals the negative k, same k we've been talking about, times t of however long that interval was. So ln is the natural log. At time t, the concentration of RT is going to be less. This concentration is going to be less than this. Time 0 is before we started. So let's just pretend like I started with the concentration of R equals 1 molar at the beginning. This is R0. So at the end, after some time has gone by, what's going to happen to the concentration of reactants? The concentration of reactants will go down. It's going to be reacting. The stuff's going away. So this is going to end up being like 0.5 molar. So hopefully if you start to recognize what we're talking about here, the quantity on the top is going to be less. So the concentration of R at time t is going to be less than the concentration of R at time 0. As a result, when I take the natural log of a value less than 1, so I don't know, of x less than 1, is going to give me a negative value. Thus, that's where this negative sign comes from. I have to be able to keep this whole thing constant. This natural log gives me a negative value on the left. I'm going to need a negative value on the right, so I put the negative sign in to make sure that we're getting that. Because time, you can't have a negative amount of time. You can't have negative 10 seconds. That would be ridiculous. And the value of k is never going to be negative either. It is a proportionality constant that's